Welcome to 2DMat, 2D Materials in Tribology. Today with Professor Dr. Babak Anasori from Purdue School of Engineering and Technology. He will talk about 2DMXenes, tunable mechanical properties and their phase stability and transformation. Before we start, we want to thank our sponsors for their support. We are sponsored by the two MDPI journals Coatings and Lubricants, as well as Frontiers in Mechanical Engineering and Arctic Instruments.
Good afternoon to everybody. Welcome to a new webinar, 2DMat, 2D Materials in Tribology. My name is Andreas, and together with Phil, we are hosting together the webinar given by Professor Dr. Babak Anasori. It is my great pleasure to introduce Babak, who's a collaborator for the last couple of years in the field MXenes and Tribology of us. So there's not much to say about Babak. Babak has received his PhD at Drexel University. Afterwards, he has been a research assistant professor in the lab of Jürgen Gotzi, the inventor of MXenes, who has given the first webinar in this webinar series. Babak is number 2 in the world related to MXenes, if you at least look at the citation statistics. So he's really one of the main experts in the fields. He has published more than 150 papers, reached more than 28,000 citations, and I think this year he's going to break the 10,000 citations mark, I believe. So I think it is an excellent opportunity to listen to one of the experts in the entire field, and we are very looking forward to the insights related to tunable mechanical properties and their phase stability and transformation. Thank you very much, Babak, for joining us today, and we are excited to listen to your talk.
Thank you, Andreas, for the kind introduction, and thank you, Andreas and Philip, for organizing this webinar series and inviting me. This is absolutely a great opportunity for everyone to learn about things related to tribology and general 2D materials and their other properties. Today I'm going to talk about 2DMXenes, about their tunable mechanical properties and phase stability and phase transformation. And also I want to mention that I'm maybe the second most published. Citation varies, so I do not know about citation, but in terms of publication, just to make one correction. And so before I start talking about my technical presentation, I want to explain to you where I am. So I'm located in state of Indiana, which is here on the map, and in the city of Indianapolis. This is the skyline of the city. And if you are into cars and racing, you might have heard of Indy 500, which happens every year in Indianapolis. And our campus is in the city of Indianapolis, and I am from the Mechanical and Energy Engineering, the School of Engineering and Technology at Indiana University, Purdue University at Indianapolis. So now to my technical part. Let me change my cursor to a pointer that you can see where I move my mouse so you can see it better. So this is the outline of my talk, and as you can tell from the title of my talk, first I'm going to talk about the synthesis, composition, and properties of MXenes. I'm not going to spend too much time because, as Andreas mentioned, the first of the talk in this series was done by Professor Jürgen Gotzi, one of the inventors of MXene, and he covered the MXene synthesis, composition, and properties very well. So I invite you to listen to his webinar if you're interested more in the composition and properties aspect. Then I'm going to talk about the tunable mechanical properties, then talk about the oxidation and stability. These two in my opinion, are very important to almost all applications of MXene, and I'll explain why. And at the end, I will also talk about the high temperature phase transformation of MXene. Something that people say, well, if it gets oxidized at room temperature, how is it even possible to be stable at high temperatures? So first start with MXene. For those of you who do not know about 2D materials, which I all know that you're here in this webinar series, so you're familiar with 2D materials. 2D materials all started from graphene, and really the boom started in 2004 and after, and now we have a whole bunch of different families of 2D materials. And one of these family of 2D materials is called MXenes. MXenes are 2D transition metal carbides and nitrides. So if you look at the periodic table of MXene, you see that we have all the early transition metals, group 3 to 6 of the periodic table, marked as green. So these are the transition metals that can be in the structure of MXene. Now, we can have 2, 3, 4, or 5 layers of the transition metals, atomic layers, and they are all have carbon or nitrogen, that's the X in MXene, between these layers of transition metals. And because we have transition metals on the surface, we have these dangling bonds that they can bond to the species available in the environment, forming surface termination shown as TX in MXene formula. And usually they are oxygen, hydroxyl, or fluorine and chlorine because of the etching environment. And more recently, you can have more variety of surface termination. This is how MXene are synthesized. They are done by top-down synthesis. So it's not a growth mechanism. First, we need to synthesize the precursor of MXene, which are usually called max phases, that they are ternary carbides and nitrides, where we have these layers of 2D, but they are bonded with a layer of A group elements, an A group element being aluminum, silicon, and others. Because aluminum or silicon and all of these A elements, they form usually a metallic bond here. We cannot do mechanical exfoliation. That's why we need to do selective etching, and I will explain how. And by doing that, we can make MXene. So first, how do we make these precursors? The synthesis is important because the way you synthesize the precursor will affect the quality of MXene. To synthesize these precursors, I'm going to focus on Ti3-AlC2, the precursor of well-known MXene of Ti3-C2-TX. To synthesize the precursor, the Ti3-AlC2, all we need to do is to combine the molar required molar ratio, meaning the stoichiometric ratio of 3 titanium, 1 aluminum, and 2 carbon of just elemental powder that you can buy from any chemical company. Then you mix it, and then you put it into a furnace under controlled environment, meaning inert gas in atmospheric pressure, and you apply take it to a high temperature where it is known to have this phase thermodynamically stable, and hold it. For example, for this phase is 1400, 2 hours, and by doing that, you can get this structure by reactive sintering of the 3 elements. These max phases have been around since 40s and 50s, and they have been rediscovered at Drexel University in the late 90s and early 2000 by Professor Michel Barsoum. That if you're interested about max phases, you can read the literature or even his textbook on max phases. These are all layered ternary carbides and nitrides. There are more than 100 max phases, and that have been synthesized, and there's a large variety of composition, more than thousands of composition in all of these different layering of the structures. When we have these max phases, then by placing them in a selective etchant, and usually, and it is something that has started in 2011 and going on since then, is usually a hydrofluoric containing acidic solutions. The hydrofluoric acid will basically selectively remove the A layer, which is aluminum here. And so we put just the powder. You see, it's a gray powder of carbide. We place it into the acid, And this is how the max looks like. And this is, we have the high resolution STM image showing layer structure, but not a 2D. Then by placing it, removing the A layers, we end up with this exfoliated structure. And you see that we have these open structure between the layers. Now they are bonded by van der Waals bonds or hydrogen bonds. Then by mechanical agitation, sonication, we can break these flakes to single flakes and have MXenes solutions. MXenes are among the ones in the 2D world that can be scaled up. And that's very important because the synthesis is a top-down method. It's not a growth mechanism. By just making this larger in terms of the reactor container and having more starting precursor mass, we can make larger quantity of a MXene film or MXene solution or MXene powder. And they behave like a clay. So the water or other cations can easily integrate into the MXene structure. So just to wrap up the MXene synthesis and properties, these are basically metallic 2D materials. MXenes have high electrical conductivity. For example, for Ti3C2 film, it has up to 24,000 Siemens per centimeter in terms of electrical conductivity. They have other unique properties that I'm not going to talk about because of the interest of time, but you're more than welcome to read the papers, or as I mentioned, listen to Professor Yuri Gugatsy's webinar on MXenes that he explained all of these very well. Now, MXenes are not just Ti3C2. They can have a different variety of composition. For example, we can have a vanadium carbide, niobium carbide, which is important when we're talking about tuning the mechanical properties. So that's why I'm mentioning the different composition here. Also, we can have these in terms of two different transition metals, where we call them double transition metal MXenes. We have two, for example, titanium and vanadium mixed together in a form of a solid solution. So we can have different of the solid solution, titanium vanadium in the 3-layer, or titanium vanadium carbide in a 2-layer, or titanium niobium in a 4-layer, and so forth and so on. Also, a unique feature of MXene family is that when we mix certain transition metals, such as molybdenum and titanium, or molybdenum and scandium, instead of forming a solid solution that I just showed in the previous slide, here, these will prefer to have ordered structure. So without doing any growth, a bottom-up synthesis, we can design these atomic sandwiches, layers of transition metals forming these ordered structures with carbon between them and covered with surface termination. So we have a really high level of control over composition, structure, and ordering of the atoms in MXene structures. Now, this is about MXene synthesis and composition. In terms of properties, and this is from a review paper that we put out in 2021, my PhD student and Andreas and I, we really looked at properties of MXene and applications. And you can see that we have the majority of applications of MXene in energy storage and catalysis, almost about 50%. Then we have electromagnetic interactions such as electromagnetic interference shielding. And you see that only a very small portion talks about mechanical and tribology, only 5%. And that 5% is not really papers dedicated directly to mechanical properties. We included those that they just investigated the mechanical properties of MXene. And they have, as I mentioned, unique properties I'm not going to talk about. So let's move to tunable mechanical properties of MXenes. If you look at the number of publications per year since the beginning of MXene 2011, discovering at Drexel University till 2020 that we looked at in this review paper, we see that there is almost nothing about tribology up to maybe 2018. And also very little was done on the mechanical properties of MXene also till 2018. And now there is a huge interest in terms of mechanical properties, and more so on the tribology part of MXenes. And also big contribution coming from Professor Andreas and his group. Now, but you might ask, why should we care about mechanical properties? There's only little done on MXenes. As I mentioned, mechanical properties and oxidation and stability are essential for any application of MXenes. So in here, we just mark the importance of mechanical and tribology properties of MXenes with respect to every application of MXenes being explored. Obviously, we are making a structure, so mechanical properties is important. And when you see it is red, it means that we think that it doesn't have that much of importance for that application. And when they are green, it means that they are very important, mechanical and tribology. And the rationale behind our analysis, we included it in the supporting information of this review paper. So you can read the supporting information to understand how we came up with this color coding of green and red in terms of importance. So mechanical and tribology properties of MXenes is very important. Now, how much do we know about the mechanical properties of MXenes? We only know 2D, measure 2D stiffness and also elastic moduli of 2 MXenes only. Niobium 4C3 and titanium 3C2. These 2 MXenes, the elastic modulus from their 2D modulus was measured. Both were done from University of Nebraska with collaboration with Drexel University, and by AFM indentation, atomic force microscopy, the 2D modulus was measured, and also based on the thickness of MXene, the modulus, elastic modulus was calculated. You can see that we are in the 300 to 400 gigapascal range. Now, if you put it into perspective with respect to all 2D materials, MXenes are maybe the 4th, 5th of 2D materials. But if you look at the synthesis route, which I mentioned that is very important, if you look at the highly scalable processes, MXenes are the stiffest of solution-based 2D materials, meaning that the materials that you can basically make them by solution processing. So they are the stronger or stiffest of all solution process 2D nanomaterials. Now, what are the key parameters that control mechanical properties of MXenes? Number one, the composition of MXene. As I mentioned, we have a variety of different compositions that we can go from titanium, vanadium, chromium, yttrium, niobium, molybdenum, all of these transition metals. And X is carbon or nitrogen, right? So depending on what composition we choose, even if we know nothing about the mechanical properties, meaning that, as I mentioned, only 2 out of 40 synthesized MXene, the elastic modulus has been measured. So how can we understand the other MXene's mechanical properties? We can simply look at the bond stiffness. How strong the transition metal with X, with carbon or nitrogen, is in MXene will determine the mechanical properties of MXene. So here we showed, again, these are all part of this review paper. We showed that by changing the transition metal, red all is for transition metal and carbon, we know that the bond stiffness will change. And from the bond stiffness, the 2D stiffness and the modules will vary. So if you're looking for something stronger, obviously, you need to go, for example, to niobium, molybdenum, or tungsten in the carbide MXenes. Now, the 2D stiffness also the same way. You can see that there is a variation. This is based on bond stiffness. This is based on calculation without any surface termination. I will talk about surface termination in my next slide. So just by playing with the composition of transition metal and carbon or nitrogen, we can tune the mechanical properties of MXene. Next is MXene thickness. As we know that we can have 2 layers, 3 layers, 4 layers, or even 5 layers of MXene. and studies, computational studies that again, if you want all of these references are mentioned in our review paper. But we summarize everything here that you can see the 2D stiffness varies based on the thickness of MXene. So this is the next key parameters that you need to keep in mind when you're designing the structure, that which MXene you need to use for the resulting, the needed, the desired mechanical properties. Next step is MXene surface termination, the TX, that as we show it, or the yellow atoms that we have it in these slide series. You can see that depending on what surface termination, whether it is oxygen or hydroxyl group or fluorine or chlorine, the 2D stiffness and the resulting elastic modulus vary. Obviously, oxygen will have one of the highest stiffness because of the nature of the bond that oxygen forms with the transition metals. So depending on what surface termination, we can tune the elastic modulus. Now, you might say, well, usually we are using the hydrofluoric acid route or LiCl hydrochloric lithium fluoride routes that we don't have control over surface termination. I want to emphasize that we can control the composition, the ratio of surface termination, just by playing with what type of etching route we go. This is from a study that was published in 2016 that showed if we use hydrochloric acid with lithium fluoride, which has a lower concentration of HF, we'll have more oxygen on the surface versus when we use a higher concentration of just HF, hydrofluoric acid, and we'll have more fluorine and less oxygen. So just by starting etching composition, etching solution composition, we can tune to some degree the surface termination. I did not have or include the new study or relatively new study that comes from Professor Talapin's group at the University of Chicago, that they showed that you can even have uniform surface termination of MXene. Just, I'm talking about the regular MXene that almost been synthesized almost everywhere around the world using the precursor of MXene, putting it into aqueous hydrofluoric or fluoride containing solutions. So by playing with the concentration or etching solution type, we can tune these, and that will significantly, look at the variation here, significantly changes the mechanical properties, the elastic modulus of the resulting MXene. Lastly, so we covered 3 key parameters in MXene mechanical properties. Number 4, it's not the last one, I have another one, but the 4 is the universal, and then the next one will be more specific. Number 4 is number of defects. Again, depending on how we etch MXene, whether we use a high concentration hydrofluoric acid, like 7 weight % hydrofluoric acid etching, or lower concentration. Each of these, while we are removing the A group elements, we also create vacancies by removing some of the transition metals such as titanium or carbon from the structure. By introducing these defects in the structure just by using higher HF concentration or harsher etching conditions, it can be higher temperature, we can create more vacancies, and that can also change the elastic mechanical properties in general of the resulting MXene. This is shown by just increasing the number of vacancies in titanium or carbon atomic sites in Ti3C2. So when you synthesize MXene, you have to pay attention to all these details. Anything that causes harsher etching, it means the MXene will be weaker in terms of mechanical properties. At the same time, in terms of stability, if you have more vacancies, I will talk about in the oxidation part of my talk, it will also cause rapid degradation of MXene. Lastly, I talk about double transition metal MXene, the double M MXenes. And here we show that when we go from single or mono M MXene to double M, for example, if we have a Ti3C2 and we change the outer to molybdenum, we can have higher mechanical properties. And tungsten obviously would be the highest. Now, these are about a single flake of MXene. You might say, well, single flake is nice, but we work with large quantity of MXene. We make a film. For making the film, all of these variables that I mentioned from 1, 2, 3, 4 apply. Plus, it also depended on how you prepare your MXene film or MXene structure, because these are individual flakes. But if you work with in the larger scale, which is usually that's the level that we need to, so we're not working with the 1 nanometer flake only, we have a stack of these flakes. Then we talk about how we order these layers together. Here's a nice study published in 2020 that showed that how you prepare your MXene film, whether it is blade coating that leads to better alignment of the flakes versus vacuum filtration. If you use high concentration in vacuum filter, then the film will be less aligned. The MXene flakes will be less aligned. That will significantly change the resulting MXene, for example, tensile strengths. So both these films were basically measured, pulled, and the tensile stress was measured. You can see the blade coated of only 1 micrometer film had the tensile strength of about 600 megapascal, but the vacuum filtered film that has this misaligned or disordered flakes had only 40. So here's the filtered film, tensile strength, and here is the blade coated film. So you can see there's huge difference between the two. And that's not just, there's no change of the nature of MXene. This is just based on the alignment of MXene. So to wrap up this section of my talk, MXene mechanical properties is tunable. And we have several knobs to play with to control the mechanical properties of MXene. It can be how we synthesize the precursor, how we synthesize the MXene with different etchants, number of defects, even the nature of the A group elements that we synthesize, surface termination, thickness, and all of that will lead to tunable mechanical properties and tunable tribology properties. As I mentioned, this was more of a review, so that's why you can find all the references in our review paper that I mentioned as a reference in this slide. Moving forward, MXene oxidation and stability. As I mentioned, mechanical and tribology is one thing for all the applications. Stability of MXene is essential for any application that you want to claim that you are using MXene. For anyone who work with MXene, we know that MXene usually, when we synthesize it, because in the aqueous solution, it gets oxidized rapidly. So it is important to prevent oxidation or slow down. Otherwise, the material that we are characterizing, they're oxides and not carbides. Before I talk about MXene oxidation, I want to emphasize that that's just a general knowledge that stability of any phase is dependent on many parameters. Its composition, number of defects, environments, mean temperature, atmosphere, and many more variables. And also bulk carbides get oxidized too. So it is not that only MXene get oxidized. So this is something that I want everyone to understand. For example, titanium carbide is known to be extremely stable. But there are studies, and maybe very few studies, that show that even TIC at room temperature in water can form oxides only up to few atomic layers. So that's why the general knowledge about TIC and other carbides is that they are stable at room temperature, or in water. But the reason for that is when, for example, before 2D materials era, we were looking at bulk, and no one really cared about 2 or 3 layers of atoms. So that's why they were called highly stable. Also, they are stable at high temperatures, but we know at high temperatures, every material will have, if they're stable, they will have a protective oxide scale around them. So everything will get oxidized. Now the oxidation depth becomes extremely important when we work with the material that only is few atomic layers. So that's why MXene oxidation becomes a major issue, and also it creates the best platform to study stability of carbides. Now, for this part of my talk, I am basically going to go over many of these extremely useful papers that I put here, and I will mention them as my references. So it is not, any of these are, none of these basically were done in my group. These are all done in other research groups at different universities, but I found them very useful when we are looking at MXene oxidation and stability. So first, when we put MXene in water, which is how we synthesize MXene, usually it reacts with water and turns into TiO2 and also methane. And this is really the result of the great work of Professor Vadim Machalin of Missouri Science and Technology, that he explained how this phase transformation happens. And here we show basically as synthesized MXene film, and after aging of 5 weeks in water in a refrigerator at 5 degrees Celsius and 10 weeks. And you can see after 5 to 10 weeks, almost everything turns to TiO2. And here's a schematic that I got again from Professor Machalin's paper. It shows that MXene goes from MXene flakes to TiO2, almost all TiO2, maybe some carbon covered around it. And here's a schematic that comes from the first oxidation study that is published in 2017 that shows that MXene oxidation starts at edges. So I want to basically make it simple. MXene in water over time will go from a carbide to oxide. This is how a MXene look like, meaning MXene film. If you put it under a microscope and you see these dotted points, these are the oxides that you see on the flake. And that is not MXene anymore. How can you prevent MXene oxidation? This is coming from the first study that basically showing that if you want to slow down or prevent MXene oxidation in colloidal solution, you can lower the temperature, meaning put it in the fridge at 5 degrees Celsius, or you can also remove the dissolved oxygen in water, meaning that if you just argon bubble this solution to remove any dissolved oxygen, you can enhance the stability of MXene. About up to 2 weeks, you will see that there is really no degradation when we have it in, we have this solution of MXene under argon at low temperature, and low temperature is 5 degrees Celsius here. And you see that there is almost no oxidation when, or very little amount when we keep it in argon. The next way to protect MXene is to freeze the MXene aqueous solution. This is another study published in 2019 that clearly showed that if you store MXene solution, you freeze it either in a regular freezer, minus 18, 20 degrees Celsius, or you use a minus 80 degrees Celsius freezer. You can keep MXene almost stable up to 5 weeks or 10 weeks. Here you see the MXene in the fridge with 5C, that almost everything turned to oxide. And here you can see that these that were kept in a freezer were both stable. Also, the other way is just to remove the water. If you remove the water, you can see that in this study, it showed that if we disperse MXene in isopropanol, even if we have oxygen, they're stable. And you can see here that this is MXene isopropanol with oxygen, that up to 30 days, there is almost no shown of change of properties. So that's another way to control MXene oxidation. Change the solution from water to isopropanol. There's another study came up from Drexel, from Professor Barsoom's group, that they showed that MXene oxidation starts from the edges, as we briefly mentioned previously. So that's the defects area. So if we can basically protect the edges, then MXene oxidation will be just prevented for a longer time. Here you can see that this is a MXene film after MXene flake in TEM after storage, that you can see all these black dots are oxide nanocrystals forming. And here's the one that was capped. So edge capping with some, for example, here is only 0.1 molar of polyphosphates. Excuse me. That they showed that these will just attach to the edges of MXene and stop the MXene oxidation. This is MXene after storage with edge capping and showed no oxidation. The other method that came out from Drexel, from Professor Yuri Gugot's group, that they showed that if we modify MXene precursor synthesis route, we can significantly, up to 10 months, improve the stability of MXene Ti3C2. The way they modified it is very clever and simple. If you change the stoichiometric ratio of the Ti3 titanium to 1 aluminum, 2 carbon, and add twice moles as for aluminum as needed, the precursor will have less defects in the structure, and that less defects of the precursor means less defect in the structure of MXene and increase the shelf life of MXene. Here you see that after 30 days, there is really no change of properties. And here are the 2 TM images of a fresh MXene, and after 10 months of Ti3C2 stored in water, and you only see small amounts of defects forming on the flake. Remember, if we are not using this modified precursor with 2 moles of aluminum, only after few days, basically, MXene will get oxidized. You can see this is something expected after a few days of regular MXene, and this is what happens if you use the excess aluminum route. So a clever way to modify the precursor, something that almost no one expected to happen, but it's really working very well. Now, all of these that I mentioned, they were all about Ti3C2 stability. If we work with other MXenes, because they have smaller flakes, they have more defects, and we have not really mastered the synthesis route of other MXene, they're more defective, and some of them are thinner, which means that they will be oxidizing even faster. Here's a Ti2C. After 1 day in colloidal solution, it is gone, oxidized and gone. Here's a V2C AFM that you see that after storage, the flakes will turn to oxide. So here is the MXene flakes, and here you do not see the MXene flakes because they're all covered with oxides and turn to oxides. Here's the MXene film, and these are again the result of work from Professor Bidagi's group at Auburn University, that they showed the fresh MXene film. V2C, even if you keep it in film, let alone the solution, after 1 month of a MXene film, V2C, it will oxidize so much that the film will deform, something that you do not see with Ti3C2. So some MXenes, such as these, they are even unstable in a dry form. How can we prevent these? A method that first started, again, from Auburn University of Professor Bidagi, and now also there's a recent study coming from Drexel University, Professor Yuri Gugotsi, showed that by addition of lithium chloride salt to MXene solution, even if it is V2C, the least stable MXene, we can create flocculation, and that will lead to improving the stability of MXene. Here's the MXene film after V2C, after 1 month, and that you see that there is really no change of the film. This is the film, and here's the solution. that you see that after more than 3 months, almost there is really no change in MXene V2C. So by addition of salt and creating flocculation, we can prevent oxidation of MXene. So these are the methods that I just wanted to summarize for everyone, that we can control MXene oxidation, whether it is removal of oxygen, change of solution, or modifying the synthesis route, or addition of different salts by edge capping or by creating flocculation. Now, moving to the last part, and I'm going to be very fast on this part because it is relevant to the topic of tribology, but it is important to emphasize that MXenes behave like almost every carbide. That we just talked about MXene getting oxidized by just few days of storage in air. Now I'm going to shift gears and talk about MXenes can be used to make ultra high temperature, not even high temperature phases. So how do we do that? First of all, if we heat treat MXene, if you want to go to high temperature for every material, if you want to avoid oxidation, you need to use an inert atmosphere or vacuum. Now, if we run it under inert atmosphere and vacuum, we can remove the surface termination. We can gradually, up to 700 or 800 degrees Celsius for Ti3C2, we can remove the OH, fluorine, and oxygen from the surface of MXene. Then it becomes a titanium carbide phase diagram structure. And we are in the non-stoichiometric phase diagram. So now we can use MXene as precursor to design novel structures that is traditionally impossible to make for high temperature materials. The first study of the phase transformation was done in 2018 from Oak Ridge National Lab with collaboration with Drexel University. It was shown that when we heat treat MXene Ti3C2 at 500 C in situ STEM in vacuum, we have homoepitaxial growth of MXene, meaning that we'll have layers of titanium carbide forming over a MXene and make it thicker and thicker. So it is basically the 1-1-1 plane, but forming these thicker layers that they are basically, we call them hexagonal TIC, because they're off of the basal plane of MXene. So there is really no oxidation when we remove oxygen, obviously, and we can create carbides. Now, in a nutshell, if I want to explain what happens to MXene when we take it to higher temperatures, when we take it to 1000 C, and this is a study that we did at Drexel when I was at Professor Yuri's group, we see that we have these layer structure at 1000 C. And when we go to even higher temperatures, we create TIC, titanium carbide. Now, the titanium carbide, so there is no oxide, there is no TiO2, we form titanium carbide. Now, the titanium carbide that we synthesize has high texture. So I'm going to skip through all this and just bring it to here, that you see that if we take it to higher, even 1500 C, the titanium carbide that we form is highly textured, meaning that we have only the 1-1-1 plane of MXene, sorry, 1-1-1 plane of TIC shown in the X-orbit, because they're growing off of the basal plane of a hexagonal structure, which is identical to the 1-1-1 plane of TIC. That's why these diffraction peaks are a lot stronger, and it is not something that you see in a regular TIC. So by the use of MXene as precursor, we can design carbides and ultra high temperature materials with the unique morphology, with the unique texture that is impossible to do in a regular route of making these carbides. So I hope that I was able to explain the 4 aspects of my talk today that I intended to do, which is MXene synthesis and composition, and the variety of different synthesis and composition. Also the stability of MXene and phase transformation at higher temperatures, and cover the tunable mechanical properties of MXene. And these two are essential. The mechanical, tribology, and oxidation are essential for any application of MXene. Before I finish, I also want to invite everyone to submit their basically nano art, which can be a microscopic image or any type of image, to the nano artography competition that we organize every year. And by submitting one image, you have a chance first to enter this competition and also to win $1,000. And it is a great opportunity for all the students basically to think outside the box and promote what they do to the public and not just in their research publication. With that, I'd like to thank my research group, my collaborators, the funding agencies. And if you're interested, if you have any question, feel free to email me, or you can find our manuscript and publications on our research website. With that, I would be happy to answer any question. Thank you.
Thank you very much, Babak, for the very comprehensive overview, especially about mechanical properties of MXenes and oxidation stability, both aspects which of course are also very important for tribological properties. And I think especially also for the people giving some hints on what one has to really pay attention to when handling MXenes. I think that's very helpful. Yeah, with that, we come to our Q&A session. And of course, you can ask your questions in the chat, things what also some people have already done. But you can also raise your hand and ask Babak directly if you want to do that. Yeah, in the meantime, we will start with a question from the chat. And the first question is related to the electrical conductivity. What is the reason for MXenes having such a high electrical conductivity?
Sure. So let me go back to the electrical conductivity. I don't have a full slide to describe it. So the best way to think about MXenes is from the bulk perspective. And that's really my favorite approach, basically looking at the literature to identify what the bulk properties have first and see whether it follows that or no, it has effects of 2D. Now, carbides are generally known to be the conductive ceramics. And that's something that has been extensively researched in the 80s and earlier and after in the 1980s. But the carbides were called basically conductive ceramics, which is unique compared to oxide ceramics that everyone is familiar with. And that's basically from the nature of the titanium and carbon bonds that creates this unique structure that they are electrically conductive.
All right, thank you. So there's a question also, somebody has raised his hand. Dip does, maybe you, if you want to unmute, you can ask your question.
Yes. Am I audible?
Yes, we hear you.
Okay. So thank you, Professor Babak, for such a nice and interesting talk. One of my concern is, so presently these MXene phases are mostly showing very good electrical conductivity. However, for any CMOS related application, we need little bit semi-metallic or mostly semi-conducting behavior. So it's basically not a question, it's a suggestion. I ask a suggestion from you. How can we functionalize these MXene phases as if it becomes more towards semi-conducting without losing the...
Go ahead, sorry, I interrupted you.
Oh, that's not...
Okay, so there are two ways. One is modifying the surface termination. So this aspect of the basically electronic properties of MXene I did not cover because I wanted, there are so many topics that we want to cover, but I wanted to focus on the topic. So there are a few ways. One is to modify the core MXene structure, meaning that it has been shown that when we go, for example, from a Ti3C2, which is highly electrically conductive, to other MXenes, for example, the ordered structure where we have chromium or molybdenum on the surface and titanium in the middle, or even solid solution where we have carbon nitride, the electrical conductivity significantly drop. So we can tune the electronic properties by playing with the composition, because when we say MXene is highly electrically conductive at this impressive number, this is only for Ti3C2. And we have right now about 40 different compositions that I have in these slides that we can synthesize. And that leads to modification of the electronic structure and the electrical properties to become more resistant. The double transition metals been predicted to be semiconductors when we have a uniform surface termination. Everything that we have measured so far, we had a mixed surface termination, so that's why we found it to be more resistant, and we did not observe any semiconductor behavior. It was more of a semiconductor-like that I do not have the reference here, but you can find it in this review paper, that there was a study that we published when I was at Drexel in 2016 that we showed that how we can tune the electronic properties of MXene by just playing with the core transition metals. We can also modify the surface termination, and that is something that till 2020, we had really no direct method of forming a uniform surface termination. But as I mentioned, by the work of Professor Dimitri Talatin from the University of Chicago, use of salt, molten salt, now we can form uniform surface termination, and that can lead to having MXenes with semiconductive behavior. So I invite you to read this paper, this review paper that I have published in MRS Bulletin, that we discuss about how we can modify the surface termination. Obviously, there are many more papers. Also, you can also read the latest review paper published by Drexel, Professor Yuri Gogotsi, published in Science, that you can learn more about the possibility of tuning the electronic properties of MXene.
Thank you. Thank you for detailed answer.
Yes.
Yes, next question is, how will MXene perform against bacteria with a higher activity than other materials?
So that's another area of MXene, and there are studies that published on antibacterial behavior of MXene. There are review papers that showed, yes, they are effective for antibacterial usage. And there are some proposed mechanism of how MXene will damage the bacterial DNA. So I invite you to read. I'm looking for a reference to give you. Probably the latest review paper, again published in Science, will have some of these, or simply just Google Scholar MXene antibacterial, and you'll find a lot of these information that in many reviews and also research papers that were published.
Yeah, for sure. There's a lot. Also, another application-based question is, what is the potential of MXenes in water absorption?
For water absorption, or
yes.
Yes, well, in general, something that I'm looking for. So let me find some slide that can explain. So here, depending on the synthesis route of MXene, for example, when we use the HCl-LiF method, we create MXene clay, meaning that they can accommodate up to few layers, 3 layers of water molecules in between the layers. And that is basically can absorb water, meaning that, for example, if you put in water, it swells to the larger volume because it can have 3 layers up to 3 more layers of water molecule in between the layers. So they can easily absorb water in between the layers. So this water absorption happens in between the layers, not on the surface. So that's why it will be so effective when you use MXene clay powder as basically to absorb water onto the surface of MXene.
Yeah, of course, this was not so application-based again. At the beginning, I thought it's water desalination. But
right, so the water desalination and water membrane in general, that's another application that I invite everyone who is interested to read the review papers or research articles about water desalination and MXene. Water membrane would be the keyword that they can search and identify a series of different papers that they can find their answers for.
Yeah. Yeah, basic synthesis question is somebody's asking that he wants to know the need to add aluminum and or silicon to the starting materials during synthesis if they will have to be etched out afterwards.
Yeah, that's a great question. So if you just put titanium and carbon, for example, together, that's something I mentioned at the end of my talk, that we form a titanium carbide, and titanium carbide is a cubic structure. So it is not a layered structure. Of course, you can argue that like this is layered, right? But they don't, so the 1-1-1 plane of FCC is layered, but the distance between the layers are all similar. So there's really little known, if any, that how we can really break these two single flakes. So that's why we would need a layered structure. To make the layered structure, we need to come up with a different precursor than titanium carbide. And that different precursor is these layered ternary carbides, which are called max phases. So we are not simply adding aluminum and leaching it out. We are adding aluminum to create a structure that is impossible to make just by using the transition metal and carbon. So by adding aluminum, we synthesize a new phase. It is not a regular just carbide. It's a ternary carbide. It's a family of carbide. As I said, you can read. There's a textbook about it that you can read about it. Now, when we form this layer structure, then by leaching out these aluminum or silicon, we can keep the 2D or layer structure that leads to MXene. So this addition of aluminum is simply to create these layer structure that we can later on remove. Now, even more relevant is the synthesis of molybdenum 2C. MO2C is synthesized by adding gallium, and you start with the hexagonal MO2C. So that is layered, you might say, which is true, but it is almost impossible, or I would say, at least for now, it is impossible to delaminate or exfoliate MO2C to single sheets. So by adding the A layer, which in that case is gallium, we create again a layer structure like this, where we have two layers of transition metal with carbon separated, spaced apart by these A layers. So the addition of these A layers is needed to create a new structure that can be used as precursor of MXene. So that's why we add the A layer and then we later on leach it out. It's a phase. It's a new phase formation by adding the A layer.
Yeah, and the second question by the same person is if there are not repulsive forces that can arise from the etching out of the aluminum layer,
so
which then could affect the bonding.
So there's not affect the bonding of the material. So when we leach out the aluminum, then the surface, titanium, for example, is available to bond. And the leaching out usually is by attacking fluorine ions to aluminum. And then the fluorine and oxygen will also attach to the surface transition metal. And that will create this now smacking the surface terminations. These will now have bonding, but not the primary metallic bonding anymore. They will have the secondary, the van der Waals bonding or hydrogen bonding if we have OH on the surface. But now with these bonding, the interaction of the surface termination bonding, they will be forming these layers still within one powder structure. So they're still into a powder. So that's, they don't really repel and go away by just leaching out. I hope that I answered your question. Trying to understand. Yes.
Sure. Then there's a question about the synthesis route. If you could give at least one environmental friendly synthesis of MXenes.
Yes. So definitely, there are now new methods emerging. For example, by environmental friendly, I think it's just to avoid hydrofluoric acid, I assume. And there are new methods emerging. As I mentioned, I don't have discussion about molten salt method, but that's a new emerging area. Although molten salt was something that we used before to make the first titanium nitride MXene, Ti4N3. But to the extent that now we have a better understanding and better control of synthesis, molten salt is something that in the past 2 to 3 years have been used to make novel MXenes and MXenes with uniform surface termination. So molten salt is another method that you combine different salts and you form a eutectic at lower temperature. You can melt it at 500 C, and that can lead to exfoliation going from max to MXene with the use of molten salt. Electrochemical etching is another that we can avoid hydrofluoric acid. So by electrochemical etching and use of HCl, hydrochloric acid, we can also synthesize MXene. So there are different routes of synthesis. And there is more coming almost every few years, and they are more, they are basically HF-free. By environmental friendly, I think that just avoidance of HF, what we mean. But in general, all of these will have byproducts. And I believe that for any scale up, as we say, and if a material moving to industry, we need to think about how we can handle the byproducts or waste. That we don't simply treat them as waste, we can also treat them as byproducts. And we can treat, for example, when we have HF, we can treat the waste that we have a sustainable method of synthesis.
Great. The next question is about the oxidative stability. How is the stability of max phases compared to MXenes?
So as I usually like to mention, that everything gets oxidized, right? Including us. So even the highest stable carbides, right? Titanium carbide, molybdenum carbide, or all the heating elements that we work with, the furnaces that we have in our labs, they all oxidize. Now, the stability of all of these high temperature phases depends on how much of a thick oxide scale we form around these to protect and prevent further oxidation. Certain max phases, such as the aluminum-containing 1Ti2AlC, is known to be stable in terms of oxidation up to 1200 degrees C because it forms a protective oxide scale around the titanium-2AlC2 as a bulk. Obviously, if you do it as powder, the oxidation will be a lot faster, and that can be done even at lower temperatures such as 500, 600 degrees Celsius. If you're interested about the oxidation of max phases, again, you can read the Max book or many of the papers of Professor Michel Barsoum that previously looked at the oxidation of max phases in different varieties of max phases at different temperatures.
Good. Then you showed that the oxidation stability is quite significantly increased when you use a molar ratio of 2 of the aluminum. And the next question is how or why the stability of this MXene is then improved.
So the exact mechanism I would say it is a novel study that it is not known, but the best way based on the findings of this paper, and this is the only paper that reported that use of 2 aluminum, is that this, when we have excess aluminum, although we form impurities such as intermetallics, but the structure of the max phase, because we have more aluminum, we have more titanium, will have less defects, less vacancy of titanium and carbon in the structure, because we know all of the carbides, including max phases or the binary titanium carbides and others, they're always non-stoichiometric. First of all, they have less carbon than we always write. For example, if you order TIC and you buy it from any chemical company, it is never is a TIC. It is non-stoichiometric, and basically it's TIC X, which X is usually 0.9 or lower or higher, 9.5 or something like that. So if we can design a method that we can make a max phase that has less of these defects, the vacancy, then we'll have a higher stability. And that's the reason behind the use of higher aluminum that leads to higher stability, because the resulting TIC layer of this max phase will have less defects, less vacancy of titanium, and that leads to higher stability. Now, as I said, this is an area for further exploration and investigation to fully understand the effect of higher usage of aluminum. And it's not fully understood yet because it's only a 1-year study, or less than that.
Okay. I would say 2 more quick questions, and then the rest can ask you more specific questions via email. So the next one is, why are nitride MXenes not as widely used as carbide MXenes?
So that goes to how we can synthesize MXenes. So the nitride MXenes are in general less stable. And that, in simple terms, is because of having the extra electron of nitrogen versus carbon, that when we want to synthesize these nitrides, usually everything dissolves together instead of having the selective etching, because the bonds are not as strong as the carbides. So that's the simple explanation. So they're not because we did not, we're not interested in nitrides, because the synthesis has been very challenging. For example, as I mentioned, the first nitride of MXenes, Ti4N3, was published in 2016 or 17, if I'm not mistaken. And that was published at Drexel. When I was at Drexel, that was when we use molten salt, because every time we tried use of the regular etching, which is hydrofluoric acid containing etching, everything would dissolve together and we will form a lot of oxides. So even forming the nitride will immediately turn into oxide. So stability is a major issue when designing all these carbides or nitrides. And now with the new methods of synthesis, such as molten salt, electrochemical etching, and others, I'm sure we can design more of the nitrides and investigate their properties. I believe that by having more basically variables in MXene, we can further tune the stability and mechanical properties for sure.
Cool. Then there are 2 more raised hands. Maybe Zahir, can you up?
Hi, thank you, Professor, for such a nice presentation. Hi, everyone. My question is related to oxidation once again. Is it possible to avoid MXenes oxidation by making its composite with different nanomaterials or growing the nanoparticle on its surface? So what are your views?
Yes, definitely. So that is one of these papers that I listed here, the oxidation and stability that comes from Texas A&M, that I did not have a chance or time to go through it. We can improve the stability of MXene by combining it with other nanomaterials or even putting it into polymers. So when when the desired application allows us, we can include MXene into polymer. I believe in this study that I'm pointing here, they looked at PVA, if I'm not mistaken, and showed that yes, you can have improved stability by integrating it. So it's a matter of designing a composite, obviously also with integration of nanomaterials. If they are something that either prevent interaction of oxygen with the MXene flakes, or they will play the role of being basically sacrificial, then you can have a higher stable MXene. So I invite you to read this paper that covers that area of MXene oxidation. I have to mention that these are not the only oxidation MXene papers. These are the ones that I basically use to put these slides together, because we don't have, I do not have a review paper on this topic, so that's why I put it together based off of these papers.
All right, last one up is Yasin. Do you hear us, Yasin? If not, then Felix also raised his hand.
Hi, can you hear me?
Yes.
Oh, thank you. Thank you, Professor Babak, for your wonderful presentation. At some point, I lost connection, and I just returned. I had left some questions on the chat. I don't know if they've been responded to. Sorry.
Yes, we had discussed your questions, so we invite you to check the video afterwards that we're gonna upload on YouTube, and then you're gonna find also the answer or Babak's answers to your questions.
Breaking.
Okay. So thank you very much.
All right, thank you.
With that, yeah, thank you very much, Babak, for a wonderful presentation and taking your time for discussing and answering the questions. As Andreas just said, we will also upload the video to YouTube. So if you want to rewatch the whole talk or in parts, you're very welcome to. Yeah, leave us a like and don't forget to hit the notification bell. We would appreciate it. Thank you very much, everyone also for joining. We will definitely keep you posted about the next 2DMAT webinar coming up. And yeah, finally, also thank you very much to our sponsors, the two NDPI journals, Coatings and Lubricants, Artec Instruments, and Frontiers in Mechanical Engineering.
Yeah, thank you very much, Babak. There have been much more questions that we were able to answer. So what I invite all the people, the questions that we have missed so far, please send an email to Babak, and Babak maybe will find some time to answer you personally, or maybe to send you some literature that will help you to figure out your question. So thank you very much. Babak was an inspiring talk. I enjoyed it quite a lot, and I learned quite a lot about oxidation stability, I can tell you.
Yeah.
Thank you very much.
Thank you for having me.
Stay safe and take care.
Exactly.
Bye,
Stay safe. See you soon. Bye-bye.
See you. Bye-bye.
We also invite you to submit your research to 3 current special issues in Coatings, Lubricants, or Frontiers in Mechanical Engineering. You can find the links to the special issues in the comment section below the video.
Introducing the most advanced universal tribometer, the MFT 5000. With a modular architecture platform design, it is a robust surface testing instrument engineered to evaluate friction, wear, mechanical properties of materials, as well as lubricants over time. The MFT 5000's open XYZ stages and wide range of interchangeable modules and sensors allows users to self-implement and add-on customization and combine several tribology tools all on one device. These diverse modules accomplish various motions for any application and are capable of speeds from 10,000 RPM to to 500 Hz oscillation. The complement sensors achieve millinewton to 12,000 Newton wide force range, with options of strain gauge, piezo, and capacitive multi-dimension force sensors. The lambda profilometer, combined with the patented inline design, coincide to analyze any surface, including glass, with ease. Because of its unique four imaging modes, the profilometer produces 3D information by creating sub-nanometer surface images automatically. A fully automated and simple software interface integrates the data, enabling researchers to design and conduct tests at nano, micro, and macro levels. To simulate real-life scenarios, the tribometer comes with several environmental control options that allows testing -120 to 1200 degrees Celsius temperatures. These interchangeable chambers are skilled in evaluating high pressure, vacuum, humidity, salt spray, and tribocorrosion conditions. Due to its multiple possible configurations, the MFT 5000 is used extensively across a wide range of industries, including oil, biomedical, semiconductor, coatings, automotive, electronics, materials, aerospace, and many more. On this platform, all types of tribology tests are possible. Our tech instruments, leading innovation in tribology and surface test instrumentation.